last lesson, we talked about exponential functions. And exponential functions were written y is equal to 2 to the power of x. Logarithmic functions are such that our x and our y values are flip-flopped. This tells me then that our logarithmic functions are one-to-one. That logarithmic and exponential functions are inverse functions of one another. When I'm looking for x values, when I'm working with logarithmic functions, I am going to substitute our y values in so that I can find the x values. To do that, I've got a set of y values here, and I'll find the corresponding x values. I'll have the values of 1, 0, 2, 1, 4, 2, half, negative 1, and 1/4, negative 2. And you can see on the right-hand side that I have this graphed for us. We can define y is equal to log base bay of x as that number y such that x is equal to a to the power of y, where our x value has to be greater than 0 and a is a positive constant other than 1. This allows us, the way that this definition is set up, in order to write a logarithmic function into using as an exponential type function. So if it's asking us in part A to find log base 10 of 10,000, we're asking ourselves 10 to what power gives me 10,000? Well, 10 to the power of 4, we know is 10 times 10 times 10 times 10 would give me 10,000. Therefore, log base 10 of 10,000 is 4. So utilizing that exponent written form will be helpful. Part B, log base 10 of 100th is equal to what? Well, I'm looking for a value of 10. 10 to what power will give me 1/100th? I know that if I have negative values, if I had 10 to the negative 2 power, we know we write that in the denominator. This is equal to 1 over 10 squared, or 1 over 100. Therefore, we know it's 10 to the negative 2 power, and such, log base 10 of 1/100th is negative 2. Find log base 5 of 125. So I'm asking 5 to what power gives me 125? Well, 5 times 5 is 25 times 5 would give me 125. So 5 to the third power would give me 125. Therefore, log base 5 of 125 is 3. Find log base 9 of 3. So I want to know 9 to what power would give me 3? Well, I know that if I were to take the square root of 9, that would give me 3. And when I'm thinking about, we have our index and our exponent, that's the same thing as saying 9 to the power of 1/2 is 3. Therefore, log base 9 of 3 is half. Letter E, log base 6 of 1 is what? Well, 6 to what power gives me 1? We know that anything to the power of 0 will give me 1. So log base 6 of 1 is 0. Log base 5 of 5 is what? Well, 5 to what power would give me 5 itself? 5 to the first power. Therefore, log base 5 of 5 is 1. That leads us to a couple of definitions on the next page here. That anytime we have log base a number of 1, it's always going to equal 0. And anytime that our base and our of value are the same, they'll always equal 1. And the next one is telling us that a logarithm is simply written as an exponent, which is what we did on the previous page. So convert each of the following to a logarithmic equation. The best part about this is how I've been saying it. Log base A of x is what? Okay. So here I'm looking at 16 is equal to 2 to the power of x. Well, 2 is our base. So that will go directly here. Log base 2 of what is 16? Again, here is our base. 10 to the negative 3 is 1/1000th. So log base 10 of 1/1000th is -3. Our base, again, is e. E to the t is equal to 70. So log base e of 70 is t. We can go backwards. We can convert from to an exponential equation. Log base 2, so here is our base, of 5 is equal to 32, and it certainly creates a true statement. Log base A of 8 equals Q. Log base T of X is M. The common log is when we have a base of 10, and the natural log is when we have a base of E. So if we don't see a base value down below here, we assume the base is 10, or with the natural log, we assume the base is E. Find each of the following common logarithms on a calculator. If you are using a graphing calculator, make sure it's set to real mode, and then round to 4 decimal places. I'm going to pop over to Desmos, and we'll see what these look like. So I've got log. I can find log under the functions button. And under miscellaneous, there's an option for log and log base A. Notice ours just has log and example 5a, so I'm just going to put log and then type in 6457778. We see that it's approximately equal to 5.8101. Let's try log of a very tiny decimal, 1234239, and we get a negative value. Let's try log of a -3. Oh dear, it's undefined. It doesn't exist. Let's go back then to our first page of the traditional parent function, if you will, of a logarithmic function. Notice that our domain is between 0 and infinity because there's a vertical asymptote here. So when I was trying to find the logarithm of -3, it doesn't exist because we are not on this side of the y-axis. Something to keep in mind. We can also find the natural log of the following. Also using Desmos, we can click the functions button and notice there's a natural log button. Natural log of 645,778 gives us approximately 13 4/10 when rounded. We can also take the natural log of tiny decimals and get one more 0 here, about -10 6/10. However, similarly, if I were to try to find the natural log of a negative number, such as -3, just like above, it's undefined because the natural log also has a domain from 0 to infinity. So it's also undefined. Let's try to find the natural log of e. So the natural log, and then again to type, we just hit the ABC and we say e is equal to 1. Similarly, the natural log of 1 is 0. Remember that when I have the natural log, its base is e. So to work through this, the base is e even though we don't see it. So e to the first power is e itself. E to the power of 0 is equal to 1. So the natural log of 1 is 0, and the natural log of e is 1. So some other properties that we just found. Sometimes it's important that we need to change the base. So if we want to change the base from 5 to 10, so from 5 to the common logarithm, this is how we do it. For any logarithmic bases, a and b, and any positive number m, we can use the change of base formula. So log base b is equal to log of a, which is the base that we want, over log of a, which is the base we want. And notice that m goes here and b goes here. A is the base we want. So find log of 5 of 8 using common logs. So we want to change this to the log that we want. We want our logarithm to be 10, our base to be 10. Our current base is 5, and our m value is 8. Therefore, log base 5 of 8, when we change the base we want is 10. We put m, which is our 8 value, over 5, which is our b value. Substituting using our calculator, we have 1.2920, and you can seriously just put that in your calculator just as we see it, and it will give you the result. I'm going to put the word or here because or we could use natural logarithms, and I'll show you how to use that on the next page. So we can also find and change the base using natural logarithms. Our a value of what we want still is 10, our b value is 5, and our m value is 8. We want our base to be 10. We could change this then to the natural log of 8 over the natural log of 5, which will also give us approximately 1.2920. Let's graph y is equal to the function, the log base 5 of x. Recall that this then is the same thing as saying this is our base, so 5 to the power of y is equal to x. A much easier way then is to substitute values in for y to obtain our x values. And our x values are given here, or using the table of values in Desmos, and then we can use Desmos to verify our graph. If we want to graph the natural log of x as itself using the table of values, we'll see the following, or substituting into our calculator. And when we graph, notice that our graph of the natural log of x, notice that the domain is from 0 to infinity, just like logarithmic ones. How does our graph change then? How can we decide how our graph is changing? So let's graph each of the following and describe before doing so how it's obtained from the parent graph of y equals the natural log of x. Then give the domain and the vertical asymptote of each function. On the right here, I have our parent function that y is equal to the natural log of x. And we're looking at the natural log of x plus 3. Notice that x plus 3 is involved inside of our function. And when we talked about transformations of functions back in unit unit 2, the same ideas and the same concepts will travel with it. So if it's inside, it's the opposite of what we see. So we are going to translate this left 3 units. So notice our point here, our point is 1, 0, has traveled left 3 units. Our domain now, because of this shift, changes from 0 to infinity. This change changes it to -3 to infinity. And we now have a vertical asymptote at x equals -3 because that shifted left 3 units with our graph. How does the graph of 3 minus half of the natural log of x change? This is also the same as y is equal to -1/2 at the natural log of x plus 3. Because that plus 3 is on the outside of our function, it's not on the inside with parentheses, this tells us that we're going to have our graph go up 3 units. And that was from the +3. Or also that half in front tells us that we're going to have a vertical shrinking. But in addition, that negative value out front, so the negative of the half part tells us that we're going to reflect across the x-axis. We just moved our graph up and down. We didn't move our graph left and right, so our domain will stay the same at 0 to infinity, and we're still going to have that asymptote at x equals 0. The original one is y equals the natural log of x on the bottom, and then this red graph is the y equals -1/2 the natural log of x plus 3. Now we have an absolute value. How does the absolute value change? Notice that we're subtracting 1 on the inside of our function, and since it's on the inside of our function, that tells us if we're moving left or right. And because it's negative, I know that I'm going to move right 1 unit from that -1. Followed by a reflection of only the negative outputs. Only the negative outputs, because of that absolute value, those negative outputs are going to reflect back across the x-axis because of that absolute value. So our points might have been down like this, but because of that absolute value tells us that we cannot have negative values, these values are only reflected across the x-axis. We're not shifting our graph up or down. We shifted it we shifted it right, so our domain is going to shift right 1 unit. So instead of being from 0 to infinity, we are now going to be from 1 to infinity. And we have a new vertical asymptote at x equals 1, shifted to the right. In a study by psychologists Bornstein and Bornstein, it was found that the average walking speed in feet per second of a person living in a city of a population P in thousands, so P is in thousands, that will be important, is given by this function. The population in Billings, Montana is 106,954. Find the average walking speed of people living in Billings. Keep in mind that I'm going to translate 106,954 into thousands. This is 106.954 thousands. This is important. If we were to put that whole thing in there, our number would be completely skewed. So I'm going to evaluate at 106.954 thousands. And when I do, I see that the average walking pace is about 1.8 feet per second. Similarly, the population in Chicago is 2,714,856. So notice we're putting that decimal right at that thousands mark. When I substitute this value in, since the population is larger, perhaps we can assume then that our rate will be faster at 3 feet per second. And then let's graph the function. So using decimals, we can graph this function pretty easily. I entered in y is equal to 0.37 times the natural log of x plus 5/100 on one line, and then I chose an appropriate window so I could see a little bit. We could also use this just as we did in the last lesson to pull some information and or find some information that we're looking for. So suppose that a sociologist computes that the average walking speed is approximately 2 feet per second. So our y values over here represent the walking speed, whereas our x values represent population in thousands. So suppose we found that the walking speed was 2 feet per second. Use this information to estimate the population. So one method we could do is the intersect method, where on one line I have the equation y is equal to 0.37, the natural log of x plus 0.05. So we have one line that has this, and on the second line we have y equals 2. We could find their point where they intersect. So we could say that the population is about 194.5 thousand or 194,500 when the walking speed is approximately 2 feet per second, I should say. The last example is measured on the Richter scale of a magnitude. The Richter scale is equal to the logarithm of I over I sub 0, where I sub 0 is the maximum intensity used for comparison. We can think of I sub 0 as a threshold intensity that is the weakest earthquake that can be recorded on a seismograph. If one earthquake is 10 times as intense as another, its magnitude on the Richter scale is 1 greater than that of the other. If one earthquake is 100 times as intense as another, its magnitude on the Richter scale is 2 higher, and so forth. Thus, an earthquake whose magnitude is 5 on the Richter scale is 10 times as intense as an earthquake whose magnitude is 4. Earthquake intensities can be interpreted as multiples of the minimum intensity. Let's say that Nepal region in South Asia on April 25th, 2015 had an intensity of 10 to the power of 7.8 times I sub 0. It caused extensive loss of life and severe structural damage to buildings, railways, and roads. What was the magnitude of this earthquake on the Richter scale? We have our R is equal to the log of I over I sub 0. It gives us that the intensity is equal to 10 times 7.8 times I sub 0. When I substitute 10 to 7.8 times I sub 0 into the equation, our I sub 0 cancels, and I have 10 to the power of 7.8. Notice that this is log base 10 of 10 to the power of 7.8. So these logs cancel each other out, and all I'm left with is 7.8 on the Richter scale. And this concludes our lesson on logarithms.